Thank you. I'm very happy to be invited to be part of this meeting. I hope that next year we'll be able to do it in person. I'll be able to meet everybody in Mexico. So today I'll be talking about non-uniform sampling and how it can be used to both speed up your acquisition of your multidimensional NMR spectra as well as give you higher resolution. I'll spend a bit of time starting off just with introducing and reviewing the basic principles of multidimensional NMR as a way of introducing NUS, and then I'll go into describing how NUS works and some of the relevant parameters. From there, I'll go into a little bit of the details of how to acquire and process NUS data in Topspin. Keep in mind these same techniques are available on Joule and Varian Agilent instruments. The same principles apply. So hopefully, even if you're not using a Bruker instrument, you'll get something out of my presentation. So quick review of basic principles of simple 1D NMR. We do something to excite our magnetization, maybe a simple RF pulse or a combination of pulses to excite our coherences of interest. We observe an FID, our intensity of the versus time, and then we do a Fourier transform of this to get our frequency spectrum. Typically, we're going to acquire a number of scans to get enough signal to noise or potentially to get the coherences that we want. Taking this to a second dimension, now we have an internal delay that will increment as we acquire multiple 1D spectra. Once we process each of these 1D spectra, individual peaks will have varying intensities. So then if we look at individual points in this 1D spectrum, we'll have an indirect intensity versus time. Take the Fourier transform of that indirect dimension, and now we get our 2D spectrum. Another way to look at that is this, where each of the dots down below represents an individual 1D spectrum. So again, we systematically increase our internal delay, acquire a series of FIDs, which allows us to get our 2D spectrum. Moving to higher dimensional experiments extends this a little bit further. Now we have two internal time delays, and we systematically increase our first time delay, or in this case labeled T2, to get a 2D spectrum. And then we continue doing that over and over and over while incrementing a second time delay, in this case labeled T1. This gives us a series of this 2D matrix of 1D spectra. Again, each dot here represents a 1D spectrum or a 1D FID. Problem with this is it can take a long time. Each of these FIDs will probably acquire multiple scans, either to get to necessary signal to noise or to select the coherences of interest. And even with 2D experiments, it can potentially take a long time to get the information that we want at high enough resolution. So it turns out we don't actually need to acquire all of these data points. By using non-uniform sampling, we only observe and acquire a subset of these FIDs. In the processing, we'll do a Fourier transform of the data sets that we acquired, and then using some very clever math beyond my math skills, but programmed into the software, the missing data points are reconstructed. Now we have our intensity versus time that we did for a normal 2D or 3D experiment, do our Fourier transform, and we get back to a 2D spectrum. So as a practical example, it's a traditionally acquired HSQC of the sample cyclosporin and benzene. Use 256 data points in the indirect dimension, which corresponds to 128 complex FIDs. 2 scans per increment, so 20-minute total time HSQC, so fairly standard acquisition. What we can do with non-uniform sampling, though, is acquire only 1/4 of these data points. So 25% non-uniform sampling, still 2 scans per increment. Now, because we've acquired only 1/4 of the data points, it only takes us 1/4 of the time. So now in 5 minutes, we have our HSQC. And just zooming into these, we can see that we really have identical quality spectra, even though we only acquired 1/4 of the FIDs. Moving to 3 dimensions or higher dimensionality, we can do the same thing. On the left, we have representation again of a 3D acquisition, where each of these points represents an FID that's acquired, where we systematically increase our internal delay T2 and internal delay T1. On the right shows the matrix where we've acquired only 1/4 of these data points. And just showing an example of ubiquitin molecule looking at a backbone experiment, the HNCO, where we're correlating the backbone amides to the carbonyl carbon chemical shift. In this case, the traditionally acquired experiment where we're looking at in the middle, just the F1, F3 projection, took almost a full day, 23.5 hours. But doing 10% sparse sampling, we're now able to acquire data with similar quality data in under 2.5 hours. So this can be an extremely powerful technique for bio-NMR experiments, which traditionally take a long time, sometimes multiple days. So far what I've described is the idea of using non-uniform sampling to do things a little bit faster. We can acquire the same data in a short enough experiment time because we don't have to acquire all the data points. But just as useful or sometimes more useful is the idea of acquiring our data with higher resolution. Or sometimes we're trying to do a little bit of both. We want a higher resolution spectrum than we could acquire through traditional techniques, but we also want to do it in a shorter amount of time than we can do through traditional techniques. And before I go into a little bit more detail of the resolution with non-uniform sampling, again, just a very quick review of basic NMR principles. That if we look at a 1D spectrum, the rate at which our FID decays gives us the resolution of our spectrum. So up top, if we have an FID which decays rapidly, this might be because of the inherent relaxation properties of our spins, or it might be because we have a poorly shimmed sample. We're going to get broad peaks. On the other hand, if our FID takes a long time to decay, then we'll get sharp peaks. Now with a 1D spectrum, we typically observe our FID until it decays to noise. So the spectrum that we get, we're going to have the inherent resolution based on that decay of the FID. Once we go to a 2D experiment or higher dimensionality, again, each data point, as I demonstrated before, showed before, each data point in this indirect dimension is a separate FID. So we're now limited by how much acquisition time we want to spend. And because of that, we rarely acquire our indirect FID until it decays to noise. So we have a bunch of signal and then it truncates to nothing. If we simply did a Fourier transform of that, we'd have these huge truncation artifacts. So what we do during the processing of our 2D and higher dimensionality data sets is we apply a strong apodization. We multiply by some function that forces the FID to decay down to 0. Then we do the Fourier transform, and now we have something without those huge truncation artifacts. Back to the idea of resolution now, again, typically for a 2D or higher dimensionality experiment, the amount of FID that we observe in this indirection is simply a matter of how many FIDs we acquire. So if we want higher resolution, we need to acquire more FIDs. So in this case, if I want to go out to 1024 data points in the indirect dimension to get this higher resolution, it means the experiment's going to take 4 times as long if we're using traditional techniques. And also just to look to see how much we can potentially improve the resolution, especially for a small molecule, look at a typical FID for just a 1D carbon spectrum. Magnetization is usually present and doesn't decay to noise until about a second later or even longer. For a typical HSQC, we only observe the FID for about 5 or 10 milliseconds. So we're really not observing the majority of this signal. If we go out to 1024 points, we get a lot more of this, and we can combine this with 25% sparse sampling, which is going to give us an experiment that takes the same duration as the traditional HSQC. So again, the traditional HSQC is represented by a series of FIDs acquired with sequentially incremented indirect acquisition times. So now if we want to go out to 4 times as long and acquire only 25% of these points, we're still acquiring the same total number of FIDs. So in this case, we have the same acquisition time, 20 minutes in both cases. But now the one where we did the NUS, we have a much higher resolution. And just zooming into these a little bit more so you can see that improvement. We can potentially push things a lot further. This next example is a bit more than I would probably do with routine acquisitions, but just showing that we can potentially do extremely long indirect acquisition times, in this case, 8K data points, and very sparse sampling, so just 3.125%. This is still going to be the same total number of acquired FIDs, so the same 20-minute acquisition time, And now we have extremely sharp peaks in this indirect dimension. Just overlaying these three spectra and offsetting the peaks a little bit in the proton dimension, just to make it a little bit clearer, we can see the vast improvement in resolution by doing the non-uniform sampling. And even a peak here where in blue for the traditional HSQC, there really wasn't any information to suggest that there was more than one peak there. But even just going to the fairly conservative 25% sparse sampling shown in red, we can see that we indeed have two correlations. And then these are fully resolved with the case where I'm doing the much sparser acquisition at with 8K data points. And one more thing looking at this data is that if we take a projection along the carbon dimension of this HSQC, which is shown below, we get our effective 1D carbon spectrum, or at least the carbons with attached protons. Above this is a standard 1D carbon spectrum acquired in about 1 hour. Again, the HSQC that I demonstrated was acquired in only 20 minutes. And we have pretty similar resolution of this projection carbon spectrum to what we have with the standard carbon, and fairly similar signal to noise acquired in a lot less time. Just as I showed for saving time, this can be applied to higher dimensionality experiments, and representing a 3D experiment where I have 64 by 64 complex points in each indirect dimension. Instead of just acquiring 1/4 of these points, I can acquire the same number of FIDs, but spread it out to a longer duration in the indirect dimension to give us better resolution. And just a quick example of a spectrum showing this, where what I showed before was this middle spectrum where we did 10% sparse sampling with the same matrix size as our traditional acquisition to get the 2.5 hour HNCO experiment. Going out to much longer, 512 complex points in both indirect dimension and 2.5% sparse sampling, we now have much higher resolution peaks, and it's still only half the acquisition time as the traditional HNCO experiment. So moving on a little bit more about how do we do NUS and what parameters are relevant. One of the most common questions that comes up is how sparsely can I sample? Now, I was talking about for the HSQC doing 25% sparse sampling or 10% sparse sampling for the HNCO, or the other case where I went to 3% sparse sampling. But how sparse you sample isn't usually the right question. Usually the question that's more relevant is how many FIDs do I need to acquire? And this depends on a number of factors. Primary factor, I would argue, is the number of expected frequencies. And this is just a matter of simple data fitting. If I'm only trying to get one frequency out of my spectrum, if I just have a single correlation, then you don't need a lot of data points to extract that. If I have dozens of frequencies, I'm going to need dozens of data points to pull out each of those frequencies. So the number of acquired FIDs needs to at least be on the order of the number of frequencies expected. There's also the question of how many scans are you going to need to achieve adequate signal to noise. What non-uniform sampling for the most part isn't going to help you with is achieving that signal to noise. I mean, there's a little bit we can do that I'll discuss in a moment, but bottom line, if I need to acquire 24 hours through my triple resonance protein backbone experiment to get the signal to noise, I'm still going to need to do just as many scans to see my signals. But I might be able to acquire those scans with NUS and get higher resolution. So there's still benefits here. There's also the question of what kind of dynamic range you expect in the peaks in your spectrum. And the reason for this is sometimes when we do our NUS reconstruction, we get a little bit of artifacts in our spectrum. Artifacts look like T1 noise. And if it's something like an HSQC of a pure compound, all the peaks we're looking for are going to be similar intensity. So if we have a little bit of T1 noise, we can probably ignore that. On the other hand, if we have a nosy spectrum where our nosy peaks of interest are much lower intensity than the diagonal peaks, then this T1 noise might make it a lot more difficult to identify our very weak nosy correlations from noise. So something like if you did want to do NUS for a nosy, which I don't necessarily recommend because of this, you would need to acquire a lot more FIDs. Whereas for an HSQC, you can get away with a lot less data, because if there is a little bit of noise or artifacts, we can usually ignore that. Also very relevant is how fast are your spins relaxing. And I have a couple slides later on showing this, but really just the idea that if we do have something that relaxes fast, such as a large protein, then we're not necessarily going to be able to extend our acquisition time in the indirect dimension because the signals will relax to 0. So that's going to change how we do the sampling. And then also, as I introduced at the beginning, we can use NUS for either faster acquisition or higher resolution or a little bit of both. So what your primary goal is there is going to affect how sparsely you sample. So again, one of the rules of thumbs, as I just mentioned, is that the number of NUS points should be at least as large as the number of expected frequencies. And here I have the word hypercomplex NUS points. What that means for a 2D experiment is a complex pair of real plus imaginary FID. For a 3D experiment, it would be 4 FIDs, real and imaginary, in each of the indirect dimensions. And again, for the idea that the number of NUS points acquired should be on the order of the number of correlations expected, depending on the experiment we're doing, we're going to need different number of points acquired. So we typically have a lot fewer peaks in an HSQC than we do in HMBC. So we're not going to need to acquire as many data points or as many FIDs for an HSQC. And then for a NOESY, both because of the dynamic range issue I mentioned before and because of the large number of correlations possible, we're not going to want to, we're going to need to acquire a lot more FIDs if you want to try doing a NOESY with NUS. Similarly, if we have a very large complicated molecule or a mixture, we're going to need more NUS points, both because of the possibility of needing having more frequencies in our spectrum. And for a mixture, especially if we're looking for trying to find correlations for low concentration components of that mixture, again, we get back to that dynamic range issue I talked about before. And just iterating what I said before, that reconstruction artifacts might be easy to ignore when we have similar intensity peaks, but when we're looking for very low intensity peaks in our spectrum, these can potentially be more problematic. And that's one of the reasons why I say that for NOESY, I typically don't recommend using NUS. Other rules of thumb, and these are kind of conservative estimates, is that if we're just trying to save time, how sparsely can we sample? Something like 25 to 50% per indirect dimension. That means for a 3D or 4D experiment, we can sample much more sparsely than we can for a 2D. And part of that reason is we don't necessarily increase significantly the number of correlations we're looking at in a 3D or 4D experiment. We're just spreading them out over more space. So we don't necessarily need to acquire a lot more FIDs to get this information. And now going back to the idea of relaxation. I started off a little while ago showing for a small molecule, the carbon signal is going to extend out for often a second or more. So we usually don't have the issue in the indirect dimension of a carbon HSQC for a small molecule of the signal decaying to 0. In this case, on the right, we're showing part of an HSQC for a proton nitrogen HSQC of a protein sample. Here I've Fourier transformed only the direct dimension. So in the indirect dimension, we have the decaying effective FID. And we can see that by about halfway through my indirect acquisition, the signal has decayed to noise. So there was really no point in acquiring this data on the top half of the spectrum, that I'm really just acquiring noise there. So it only really makes sense to set my TD or the number of FIDs in the indirect dimension to stop where I'm no longer getting signal. But something else that we can do with NUS that can really help in a situation like this is instead of just randomly sampling points over this region where we're acquiring data, is we can weight our sampling scheme so we have more FIDs acquired with a shorter evolution time, so we're going to have more signal to noise. So we need these points down here because that's where we're going to get a good signal to noise. We want to acquire some points further out where it's going to allow us to get the maximum resolution based on the relaxation properties. But again, by acquiring more data points where we have more signal, we're essentially going to get more bang for our buck. We're going to get more signal in less time by weighting our sampling scheme that way. And just showing what a sampling scheme for a 3D experiment might look like when we do that. In this case, we're weighting the sampling in the T1 dimension, but not in the T2. And the sampling schemes, depending on what kind of experiment you're doing, what sort of relaxation properties you have, you can have this T1 weighting or T2 weighting in one or multiple indirect dimensions. Another thing about deciding how sparsely I can sample is that we don't necessarily need to decide how sparse to sample before I start the acquisition. So one of the features of most NUS sampling schemes, and certainly other ones that are by default done in TopSpin, is that the sampling schemes are not only sparse, meaning that we skip a lot of data points, but they're also random. So unlike the traditional 2D experiment where we incrementally and sequentially increase our indirect evolution time, with an NUS data set, we jump around all over the place. So I've got a little animation to show this, where once we start the acquisition, we start at the first indirect evolution point, but then we start jumping all over the place. And what that means is if I stop the acquisition sometime later on, before it's come to a completion, all the points shown in green here represent the FIDs that have been acquired. So we have a full NUS spectrum at this point. We don't have the number of data points, the number of FIDs that we initially set it up to acquire. It's now more sparsely sampled than we had planned, but we do have a full data set that can be processed and will give us the full resolution in each indirect dimension. And when I mentioned stopping the experiment, we really don't have to stop the experiment to do this. We can let the experiment continue to run, process the data that we have. If the spectra look good enough, then we can halt the experiment. Or if we decide that we still need more signal to noise, or we have NUS reconstruction artifacts, we can let the experiment go through to completion. So it's a very useful way if you're going to be checking in on the spectrometer while the acquisition is in progress, how much NUS sampling, sparse sampling can I get away with? So just set it up for more than you need and just check on it and stop the acquisition when you're through, when you decide it's good enough. There are some new automated tools for doing this that I'm not going to go into, but it's something that potentially can be automated as well. So again, reiterating some of these themes of not only how sparsely can I sample, but what kind of samples and what sort of experiments do I want to use NUS? If I have a small molecule sample and I'm doing HSQC of a fairly pure compound, that almost always NUS can benefit us. We can get higher resolution in less time than we can through traditional techniques. Similarly, with a protein sample, if we're doing a triple resonance backbone experiment, then we can often benefit significantly from this. And again, by getting the data in less time or getting higher resolution than we can through traditional techniques. If we have the situation where we have fast relaxation, meaning as I showed before, we can't extend our indirect evolution time significantly, and then we also have low sensitivity, then NUS is going to be a bit more challenging to give us any benefit. Because of the low sensitivity, we're going to need still a large number of scans and a long duration experiment to get observable signal. But as I showed before, we can potentially weight our data towards the shorter evolution points. So we can still acquire the same number of FIDs, but we have, on average, better signal to noise in those FIDs. So we can still get something out of NUS in these cases. And then again, to reiterate, if we have a mixture with a lot of varying concentration species, or if we're talking about a NOESY where we have a huge dynamic range between the peaks we're trying to see of interest and the diagonal, then NUS is probably not a good candidate. So I now want to go on and spend just a little bit of time showing how to do this in TopSpin. My apologies to people who are using Joule or Varian Agilent instruments. I want to make sure that people who are using a Bruker instrument know how to set this up in that software. Again, all these techniques can be done just as well on a Joule or Varian instrument. The details of the parameter names and what flags to turn on is going to be a little bit different. And I apologize to Magritech and other benchtop instruments. I'm not personally aware of whether or not those instruments are set up or that software is set up for non-uniform sampling. So anyhow, with TopSpin, acquisition and processing for NUS has been built into it since TopSpin version 3.0, which goes back more than 10 years. The processing, though, there have been continued advances within the TopSpin software, more processing options, improved processing algorithms in the more recent TopSpin releases. So the first thing about acquisition is, how do I do it in TopSpin? And at the simplest level, it's trivial. Any standard parameter set in TopSpin 3.0 for 2D and higher dimensionality, simply create a data set loading that parameter set, go into the acquisition parameters tab, and then this parameter FN type, simply change it from traditional to non-uniform sampling. At this point, it's now set up to run NUS. We probably do want to look a little bit more about the NUS parameters. The TD, which corresponds to the total number of FIDs in the indirect dimension. For a traditional acquisition, this says that we're going to have 256 FIDs, corresponds to 128 complex points. For NUS, this is the effective number of FIDs that will be acquired after the reconstruction. So we're going to be acquiring only some percentage of these. Something that can be important to look at is the acquisition time in this indirect dimension. So we can just get an idea of, if we have a rough idea of the relaxation properties, how large the TD is going to allow us to acquire in this indirect dimension. If we then scroll down in the acquisition parameters to these NUS parameters, we get both the NUS percentage and the NUS points. So we can set these, either of these. Again, the NUS points are the complex or the hypercomplex points, meaning it's the real plus imaginary for a 2D experiment, or it's the real plus imaginary in both dimensions for a 3D experiment, and so forth. So something else when we're setting up the NUS sampling scheme is we have the show button, which allows us to see graphically the NUS sampling. And once you start the acquisition, this is updated real time. So as I showed in the animation earlier, it changes from blue to the data points that are still need to be done to green after they've been acquired, and then the active one is shown in red. In earlier versions of TopSpin, you needed to start the acquisition to see this at all. In the latest TopSpin release, once we set up the parameters, before we start the acquisition, we can click calculate and then show and see the sampling scheme before we start things up. And then going just very quickly into a little bit more details. In the experiment number directory for the data set, once we do this, a file is created called NUS list, which is simply a text file with the indices of the FIDs that are going to be acquired. 0 corresponding to the first FID for a traditional method, and then numbered sequentially after that. And just, again, an example of what a 3D sampling scheme looks like. The NUS list file now just contains a list with a pair of numbers for which FID in both the direct and indirect dimension is being acquired at each point. I talked about the T2 weighting earlier. That can be useful, especially if we're going out to extremely long acquisition times for a small molecule, or can often be very useful for a biomolecule, which is going to relax a lot faster. The default value for this NUS T2 is 1 second. Because the acquisition times in the indirect dimension are usually more on the order of tens of milliseconds, 1 second is infinitely long relative to that. So 1 second really effectively means no weighting. So some rules of thumb for setting T2 is, one is that if we have a constant time experiment, in that indirect dimension, we don't expect our FIDs to decay. So keeping a value of 1 is useful there. If there's no visible decay in the intensity during that indirect evolution, then there's really no benefit of doing this T2 weighting either, so keep it at 1. However, if we do see attenuation in the intensity as we go through our indirect dimension, if we happen to know the T2 relaxation rate of our molecule, we can set it to that. Or what I find useful to do is look at the acquisition time, as I showed in the previous slide for that indirect dimension, and set our T2 weighting to about this value or maybe half that value. And then that's going to give you a noticeable weighting of the data points towards the shorter evolution times. Moving on to processing, in a way, this gets a little bit more complicated because there are a lot of different ways to do the processing. There's multiple methods built into TopSpin. We have initially implemented in TopSpin 3.0 was just this multi-dimensional deconvolution, or MDD. Subsequent versions, we implemented CS, or compressed sensing. Within CS, we have a couple of algorithms as well. And there's also a lot of ways of processing your NUS data outside of TopSpin, and just some research groups that are actively working on this, and their websites have information of doing that processing. For processing within TopSpin, I first want to mention a little bit about licenses. When we first introduced non-uniform sampling in TOPSPIN 3.0, we required an additional processing license for NUS for any NUS data sets. You could still acquire NUS data without any additional license, but to process it in TOPSPIN, it required this additional license. But as of a couple of years ago, starting with TOPSPIN 3.5, patch level 3, we now no longer need a special license for processing 2D experiments. So simple 2D experiments for the last couple of years, if you have this version of TOPSPIN or newer, does not require that special processing license. You don't necessarily need this on your spectrometer, but whatever computer you're using to process your data, if you want to use process.NUS for those 2Ds, it doesn't require that license. But even though it was available in 3.5 patch level 3, make sure that it's updated at least to patch level 6. I kind of joke that we had a special feature built in that once you started processing your NUS data, it gave you time to go out and get an espresso and relax for a little bit before you had to come back and see your data. But in reality, there was a little bit of bug in the code that sometimes it take up to an hour to process a 2D data set. So clearly there was something wrong. We fixed that problem. So now 3.5 patch level 6 and newer, it usually only takes a minute, if that, to acquire, or rather to process a 2D data set with NUS. So again, with the newer versions of TOPSPIN, 2D processing is free with one particular reconstruction algorithm. There are other algorithms built into this that do require the license, and any 3D or 4D processing within TOPSPIN does require still that additional NUS processing license. If you're using NMR pipe or something like that to process your 3D or 4D data sets, you don't necessarily need to worry about this. You can still acquire the data in TOPSPIN without that license, and then take it to NMR pipe or whatever your other processing software is. So now that we're done with all that, it's great information, but what do I really need to know? And after that, the processing is actually pretty easy within TOPSPIN. When you acquire an NUS data set within TOPSPIN, the TOPSPIN data set has all the information that TOPSPIN needs to know that this data was acquired with non-uniform sampling. So when you tell it to process with just your standard 2D or ND processing commands, it knows what to do. So for a 2D data set, XFB is the standard 2D processing command. And something that happens commonly, I just told you 2D processing is free. Most of the parameters are set, you don't need to worry about it, but sometimes you'll get this message about no license being available. And this goes back to the idea that basic 2D processing is free. Some of the other 2D processing algorithms do require a license. And unfortunately, some of the standard Bruker parameter sets have the processing parameters for NUS set up to use those more advanced processing methods. Fortunately, what the message actually says is that we don't have the license available for the processing that is set in your data set, but we will process it anyways using these changed parameters. So if it's just something that you're doing by hand, you get this message, you can just ignore the message. On the other hand, if you're doing things in automation or you really don't want to see this message or have to explain to a bunch of users who you've set up to use non-uniform sampling, we can get rid of this message by just changing the relevant parameters. And those parameters are listed here in the message, this MDD_CSAlg and MDD_CSVE, just change those in your parameter set. If you look at the processing parameters tab in TOPSPIN, these parameters don't actually show up in here, but we can set them by the command line. One thing we do want to make sure that this MDD mode is set to CS. Again, this is for 2D using free processing. And then at the command line, just type in the name of these so-called hidden parameters, and it'll allow you to change it to the IST for the MDD_CSAlg and false for the virtual echo option. If you're using TOPSPIN 3.5 or 3.6, the same parameters apply, although the message that showed up did not give the full name of those parameters. So if you see this message in 3.5 or 3.6, remember it's MDD_ these names to change it. Once you've changed it, you can now save the parameter set, and then each time you load that parameter set, it's going to have the values already set for the free processing, and you won't see that message again. Last little thing about processing for 2Ds, it's not uncommon when you first process a 2D to have something that needs phasing. So here we have a 2D spectrum. We have the green negative correlations or contours on one side, the positive contours shown in blue on the other side. So we need to phase correct the direct dimension. If we use the manual phase correction mode within Topspin, highlight a couple of points that we want to phase in the direct dimension, click the R button. If we do this for NUS, we're gonna get this message that we can't phase, that we don't have the imaginary data. Part of the processing for the NUS is that it throws away the imaginary data in that direct dimension as part of the processing. Other than this phasing, it's not really needed later on. So I'm not sure if it's a matter of saving space or some other reason, but this gives us initially a small hangup, but it's not really that big of a deal. There's a mathematical function known as the Hilbert transform, which relates the real data in the NMR spectrum to the imaginary data. So all we have to do is apply this Hilbert transform to recreate the imaginary data. If you're using a Topspin user interface under the Process tab and Advanced, we can go down to Special Transformations and find the Hilbert transform, or just XHT2 in the command line. And after we've done this, the phasing works as planned. One last little bit about phasing is that if we've done this, if we've done the NUS reconstruction and gotten an out of phase spectrum and then applied the phase correction, there's often some artifacts on the sides of the peak. NUS does a much better job of reconstruction when the individual FIDs are phased properly before the NUS reconstruction is done. So if you've done the phase correction like I've shown here, I'd go back and do XFB again to redo the reconstruction, and you're going to get a much cleaner spectrum. One last bit that I want to go into is to demonstrate that there are potentially other uses for non-uniform sampling. Primarily, as I talked about, acquiring data with shorter acquisition times or with higher resolution are really the first things that non-uniform sampling was talked about. But something else we can potentially do is if we have a data set with some corrupt FIDs, we can use non-uniform sampling processing to correct this. So here I'm looking at a series of FIDs for a 2D spectrum, and something has happened at a couple points during this. Maybe it was a matter of we have some sort of a hardware glitch that shows up at random, and as we're acquiring our spectrum, every so often, just something goes bad and we get a spike in our FID. Or maybe it's something as simple as, the nitrogen doer just arrived for doing my nitrogen fill and somebody wheeled it right next to the magnet before they realized an acquisition is in progress, which caused your water suppression to go bad, and you got some spikes in your spectrum because of that. If we take something like this with these corrupt FIDs or these huge spikes in our indirect dimension, we're going to get a lot of artifacts in our 2D spectrum if I just do the standard 2D processing. But something I can do with NUS is pretty much just trick the software into thinking that this data set was acquired through NUS, create an NUS list representing all of the good data points, remove the damaged FIDs from our spectrum as if they didn't exist in the first place, and then tell Topspin or whatever processing software you're working with to process the software. It'll do the NUS reconstruction and give you a nice, beautiful spectrum. So with that, I would like to say muchas gracias por su atención, and